Hello, my name is Charlie Fite. I am a rising senior meteorology major at the University of North Carolina at Charlotte. Today I'm investigating elevated concentrations of dimethyl sulfide, DMS, in the Coachella Valley. Our methods for this research consisted of taking whole air samples throughout Southern California on the NASA C-23 Sherpa research aircraft. Once we collected those samples, we went back to the Roland Blake laboratory to analyze the samples with gas chromatography. Gases such as carbon dioxide were measured using the thermal conductivity detector, and gases such as carbon monoxide and hydrogen were measured using the reduced gas detector. So what is dimethyl sulfide? It's also known as DMS. The chemical formula for dimethyl sulfide is C2H6S, and it's the most abundant biological sulfur compound emitted to the atmosphere. It has a variety of sources. However, the primary source is our marine environments through phytoplankton and algae. And there are also terrestrial sources such as agriculture and dairy farms. So why was DMS important to study? So the oxidation of DMS leads to the formation of sulfate aerosols. And sulfate aerosols can contribute to particulate matter and potentially increase and influence local air quality with like aerosols such as PM2.5 and actually affect climate as well. So my study area here is the Coachella Valley, right near north of the Salton Sea, just southeast of the Los Angeles Basin. So what I noticed was while during our flight under 2,000 feet in the boundary layer throughout all of the flights taken this year, while on land there was an average DMS concentration of about 12 pptv. However, right here in the Coachella Valley, just north of the Salton Sea, we saw an average of about 30 pptv of DMS and maximum concentrations reaching as high as 63 pptv. And this is pretty high for what we normally would see on land. One thing I also noticed doing further analysis, I actually saw by using different air quality monitors throughout the Southern California area, I plotted and interpolated the PM2.5 concentrations. And as you can see, there's increased concentrations right here in the LA area, as well as centered right here around the Salton Sea. And it makes sense to see PM2.5 here in the LA area. However, this area around the Salton Sea is pretty rural, so it's pretty interesting to see that there's a correlation. The only thing is that this year during SARP, we didn't measure aerosols, and so I can't make a specific mathematical comparison to see what the potential the DMS had on that PM2.5, but it's really interesting going forward to look into. The meteorologist in me, of course, wanted to look and see where this air mass was coming from, and so using the NOAA HYSPLIT model, I did a 24-hour back trajectory at 500 meters, beginning at 3 p.m. By the Salton Sea on the day of our flight, and that's about when we were flying through the Coachella Valley area. And as you can see, the HYSPLIT model indicates that the air mass originated over the ocean, entered through the Los Angeles Basin before eventually getting to the Salton Sea. So one would think, since DMS can be emitted from the ocean, that potentially maybe our increased values were caused from marine sources. However, I was able to tease out the ocean as a source of this DMS for multiple reasons. One, because the HYSPLIT model indicated that there was really far travel of that air mass throughout the day. And second, when you take the ratio of ethine and carbon monoxide in the Coachella Valley, you get values of about 0.9 to 1.25. And this indicates an aged air mass. Any value below 2 is typically considered an old air mass. And DMS only has a short lifetime of 1 day because it reacts pretty quickly. And so it is most likely that the source of the DMS we were seeing was not emitted from the ocean. To expand upon that point further, as you can see, I interpolated the concentrations we saw here in the agricultural area north of the Salton Sea. And there's a pretty stark increase going southward from about 2 pptv to 60 right as you get closer to the Salton Sea. So this helps you see the gradient of the DMS and that it was most likely a local source. Also, by using the wind speed and wind direction data from the flights, you can see within the valley itself, while we know the air mass came from the LA area, there was lots of variation when we were flying through in the wind direction and the wind speeds. However, there is a bit of a stronger southerly component seen here, and south of where we were flying was the Salton Sea, so I wanted to look in to see whether the Salton Sea could have emitted that DMS. So I used methyl iodide as a comparison because methyl iodide is typically known as a marine tracer to DMS. So if they correlate strongly, you can pretty much tell that the DMS is most likely emitted from the Salton Sea in this case. However, before doing that, I wanted to make sure that I could use the methyl iodide as a tracer. And so I used the 2014 ground samples that they took of the Salton Sea as seen here in red. And you can see there are extremely high values of DMS right there near the ground and higher values of methyl iodide. So this can be used to say that we know that when we're really close to the Salton Sea, there are extremely high values of DMS. And here plotted in blue is the values from this year. And there's a moderately strong R-squared value of 0.57, indicating that some of the DMS was emitted from the Salton Sea. However, since there wasn't an extremely strong correlation, we can tell that there's also potentially other sources in the area. So I went to look into the terrestrial sources. And so right here north of the Salton Sea, there's dense agriculture. As you can see in red, there's miscellaneous fruits and vegetables, and the other main crops in the area are citrus and grapes, as denoted here. So I was able to look into citrus farms, and I actually was able to tease this out as a source as well, because when we took a ground sample at an orange field, beta-pinene is typically known as a good indicator of citrus, and we saw extremely high values of about 1,400 pptv and a lot lower values of DMS of about 5.3 pptv. Whereas during our flight, we saw 30 up to 60 pptv for DMS and a lot lower beta-pinene. And so this indicates that the air mass we were flying through was not highly influenced by the citrus farms, and so most likely was not the source of the DMS. Next, I looked into the grapes, since there were a lot of grapes in this area too. And I noticed that vineyards also emit DMS, ethanol, and CO2 during the fermentation process. But since CO2 is a really common gas found in the atmosphere at high concentrations, I wanted to make sure the air we were looking at, the CO2 that we were looking at, did not come from the Los Angeles Basin area. And so I plotted here the CO2 from the Los Angeles Basin cans that we took to a pretty well-known urban tracer, which is a refrigerant called HFC 152A. And you can see this is generally what the air was indicating in the Los Angeles area. And so you can see there's a pretty good influence, the urban influence there in the Los Angeles area. And in the Coachella Valley, you can see the refrigerant and CO2 do not correlate very well. And so this is suggesting that the CO2 in our area is most likely more biogenic. And so I used that to go into further comparison with ethanol to see if there's a correlation with grapes. As you can see, there's a not very good R-squared value of about 0.33, indicating that the grapes most likely did not have a large contribution on this. If they did emit some of the DMS, it most likely was not causing some of the elevated values that we saw. One thing I noticed further was that when looking back at 2014 during that NASA SARP campaign, a past student, Eric LaBelle, observed average DMS concentrations in the Coachella Valley of about 10 pptv. And these were high values for him, and he was excited about it. And we saw values, as we mentioned earlier, as high as 63 pptv. So I wanted to look into see what maybe potentially could have caused that increase. So when you look at 2014 of the crops here, and you actually compare it to 2016, you'll notice an increase in the crops. And you go back, and especially if you look here at the blue in the aquaculture, you see a pretty big increase. And so going into the numbers, you see that all of these crops did have an increase in that 3-year span, and most of them did not increase that much. However, aquaculture, while it did have one of the smaller acreage sizes, it actually tripled in size in just 3 years. And so that's really interesting to see what potentially that could have an effect on. And so I looked further into aquaculture. And I know, and if you don't know what aquaculture is, it's basically fish farming, where they raise fish in high quantities and sell them for commercial purposes, especially throughout the California area. And there's a high density of fish in these ponds, and so this requires necessary artificial aeration of the water and a need to separate a lot of the waste in that nutrient-dense water with electro-water separation. Electro-water separation, basically, it's a low intensity electric pulse that's into the water, and it creates these clouds of microbubbles that brings some of the waste, like the solid algae, and it brings ammonia to the surface so that they can get rid of it easily. And this is what they actually use to improve their water quality. However, I think this could potentially be influencing the local air quality. As you can see, the DMS here, we were not able to exactly measure, so we didn't take a ground can here, so I want to go further into that. And since we saw such a big increase in aquaculture, I noticed the industry as a whole is supposed to increase by 33% between 2012 and 2022. And by 2024, projections suggest aquaculture will make up 50% of U.S. seafood consumption. So it's growing fast, and I think we really need to look into this. So conclusions, elevated DMS was seen in both the Salton Sea, and I think it's because of the Salton Sea and the dense agriculture in the area. And understanding ways to rule out some of the sources, like the citrus farms and the vineyards, helps us get a better understanding of terrestrial DMS and its implication that it could have on sulfate aerosols if we were to measure those. And then fish farms produce a lot of waste and algae, and so that stark increase in aquaculture between 2014 and 2016 could potentially have influence on DMS concentrations. So future suggestions, I think they should take more ground samples in vineyards and at the fish farm so we can get a better gauge for what's happening, and also to fly over the Salton Sea so that we can get a better gradient since we didn't fly over the Salton Sea specifically this year, so we can see what has happening on land versus over the ocean itself. And then also to measure aerosols again so we can make a better comparison to see what potentially contributions DMS could possibly be having with the PM 2.5. So I'd like to acknowledge soon-to-be Dr. Stacy Hughes, Dr. Don Blake for his guidance, and the Roland Blake Laboratory for helping us look at our gases. And then, of course, Dr. Emily Schaller and Dr. Melissa Yang for helping put this program together. And then Dr. Mustafa for helping me with MATLAB and just life advice in general. Dr. Glenn Wolf for some of his instruments on the plane. And then the WASP group for their support. And then the Sherpa pilots for helping us get safely on the ground and collect our data. And also the NSERC and NASA for helping us have this amazing opportunity.